Okay, this is week 5, and we will be solving examples on the derivatives of inverse trigonometric functions. Later, we will look at some related rates problems. And then, in the last part, we will talk about linearizations and differentials. This is the agenda for today. Let me start with the first example. It is an example of the derivation rules of inverse trigonometric functions. Okay, I want to start with a recall here. Let's recall derivation rules of inverse trigonometric functions. How do we derivate, for example, arctangent x? The rule is 1 over 1 plus x squared, right? Derivation rule for arcsine x is 1 over 1 minus x squared square root, and the derivation rule for arc secant x is 1 over absolute sine of x, x squared minus 1. And there are also other 3 functions, including arc cotangent, arc cosine, and arc cosecant. Their rules are almost the same like these 3, but with an extra minus sign. Let me write them too. Arc cotangent x is the same rule, but you don't forget to put this minus sign. For arc sine x, you pretty much apply the same thing with this extra minus sign here. And for arc cosecant x, it goes like the same, x squared minus 1, but with this extra minus sign. So this is the trick here. If your function includes, sorry, this is not arc sine, of course, this is arc cosine. If your function, if your inverse trigonometric function includes co somewhere, you put these extra minus signs. Okay, these are the rules. Now let's concentrate on the first example. Here, y function can be rewritten as a power function, right? This is arc sine x to the power minus 1. Now we are ready to derive it. You first try to handle the power. You take the power down and then you subtract 1 from the power, and according to the chain rule, you need to multiply with the derivative of the insider part. What is the derivative of arc sine? And we give it here. The rule goes like 1 over 1 minus x square root of 1 minus x squared. So that's it. We first take the derivative of the power like that, and then according to chain rule, we multiplied it with this part, which is the derivative of arcsine function. Okay, next. Here we have a product, and we will apply product rule to take the derivative. Derivative of the first expression, which is x, is 1 times the second, plus x stays the same times the derivative of the second part. How do you derive arctangent? You start with the outer function, so it goes like 1 plus 1, 1 over 1 plus, you see, I inserted directly square root here. Whatever you see inside arctangent should be inserted for this x here, okay? You square it, and then according to the chain rule, you need to multiply it with the derivative of the square root function. Square root of x is derived as 1 over 2 times square root of x. Okay, so this whole part is in fact the derivative of arctangent square root of x. Okay, it is derived like this. Any questions about this part? And since we have a product here, we applied product rule. Okay, if no questions, I want to move on. And here I want to make a warning. This is the notation of your course book, which I don't prefer to use. Okay, let's put notation here. So your course book uses this notation for arctangent x. I am using arctangent x notation, and your course book uses tangent to the inverse notation. Okay, be careful. This doesn't mean that you are taking the minus 1 power. No, this is not correct. In fact, this means inverse of tangent. So it is arctangent x. This is your course book's notation. So let's start taking derivative here. Derivative of arctangent is 1 over 1 plus square of whatever you see inside, right? Like that. Minus 1. And then you need to multiply with the derivative of this square root function inside. It goes like 1 over 2 times this. And then you move one step further and you need to multiply with the derivative of this green part, which is 2x. Plus, now the second part. This is arc cosecant, and its derivative is taken by minus 1 over x squared minus 1. But since this information is given here, x is greater than 1, you can easily remove this absolute sign. Because x is positive, you don't need to use absolute sign for it. Okay, like that. I move on. This is our cosine function, and the first derivative is 1 over, how do you derive arc cosine? Remember? So here it is, 1 over square root 1 minus x squared, and also with a minus, 1 minus whatever you see inside, square it, and then you need to multiply with the derivative of this insider part. What is the derivative of e to the power minus t with respect to t? Here we are taking the derivative with respect to the independent variable t. So exponential is derivated as itself times the derivative of the power. Okay? This comes from the derivation of the insider part. Okay, and be careful, I use this minus sign here because it is arc cosine. So let's move on. Any questions on this one? Okay, let's move on. Now 33. Y prime. Okay, I need to start by derivating ln function. ln is the most outer one. So it goes like 1 over arctangent x, this is arctangent x, times the derivative of the insider part. The insider part is arctangent function, so I will use the derivation rule for it like this. This comes from the derivative of arctangent x part. Okay, like that. And then we can try 36. Okay, y prime. This is arcotangent. So apply the rule for arcotangent. Minus 1, 1 plus 1 over x squared times the derivative of this insider part. How do you derive 1 over x squared? It is in fact x to the power minus 2. So minus 2 comes down. You subtract 1 from the power. The first part is done. And this is arc cosine. How do you derive it? It is minus 1 square root of 2x squared minus 1, right? Sorry, 1 minus 2x squared, I should have written. 1 minus 2x squared times, now I need to multiply with the derivative of this part 2, which is 2, okay? Any questions on this part? First, we derivated arcotangent, and then we moved to arccosine function. So let's move on with 37. Sorry. Okay, 37. So this is arcsecant. That's why I will be taking the derivative of arcsecant function first. How it goes? It goes like 1 over absolute sine of whatever you see inside, and then this is the insider part, square it, minus 1. This is how you should handle it, right? And then since e to the power minus x is something always positive, you can just write it without the absolute sign like this. And you keep multiplying with the derivative of this insider part, e to the power minus x. How you derive it? Itself times minus 1. This part comes from the derivative of this expression. Is that okay? Let's also handle the next 138. So y prime is Now I am derivating this, which is an exponential function. So it is derivated as itself arctangent x squared plus 1 square root itself times the derivative of the power. Okay, let's write this. Arctangent x squared plus 1. This is the power. I will multiply it with the derivative of the power like that. And what is this? Now, I am using the derivation rule for arctangent. It goes like 1 over 1 plus x squared plus 1. You will square it, and then you will keep multiplying with the derivative of the square root function. It goes like that, 1 over 2 times itself. And then finally, you can multiply with the derivative of this most insider function, which is 2x. Right? Is that okay? Any questions so far? So we are using the derivation rules of inverse trigonometric functions here, and also lots of chain rules. Okay, let's move on, if no questions. Can you hear me clearly? You were so silent.
Yes, teacher.
Okay, you are there. So let's talk about related rates problems a bit. Okay, for each related rates problems, we will be following some strategy to solve it. First of all, we will read the statement, and then we will make a diagram like what is given, what we want to find. And then there are more steps to follow. Let me show you on the way. First of all, we have this problem, and let's start reading the statement to decompose what we want to find, what we are given. A balloon is rising vertically above a level, straight road, a constant rate of 1 feet over second. Okay, there's an information given here, 1 feet over second. What is this? This is the vertical velocity of the balloon, right? And in the picture, we are already given some variables. Since this vertical distance is changing in time, it is denoted by y of t. Since the horizontal distance, it is the distance of this bicyclist to the origin, since it is changing in time to be denoted by xt. And the given quantity 1 feet over second is what? It is the vertical velocity of the balloon. That's why it is the rate of change of the balloon per second. So 1 feet per second. You see, this is given. Given that, okay, let me write. This is the rate of change of the vertical distance. So it is the first derivative of y function with respect to time, 1 feet over second. Okay. What else? Just when the balloon is 65 feet above the ground, a bicycle moving at a constant rate of 17 feet per second passes under it. Okay, what we are given here. So just when the balloon is, okay, balloon keeps rising, right? When this distance is exactly 65 feet, it says that the bicycle passes under it, okay? And it is the velocity of the bicycle is also given, right? 17 feet per second. This is also given. So what is that? It is, in fact, the x over dt, right? The rate of change of x with respect to time is given as 17 feet per second. Okay? So, right that moment, dx over dt is 17 feet per second, and dy over dt is 1 feet per second. Okay, now up till this point, I summarized the question. Now, what we want to find, how fast is the distance s of t between the bicycle and the balloon is increasing 3 seconds later? So what do we want to find? By the way, let me do this diagram once again here. So, given that, we want to find. Okay, dy over dt is 1 feet per second. This is given. dx over dt is given as 17 feet per second. This is also given. And we want to find how fast is the distance s of t is changing at some particular moment. So we want to find rate of change of s function, so ds over dt, at which moment? 3 seconds later. So at the time, at the moment when, at this particular moment when t equals 3 seconds, we want to find this. Okay, this is a good summary of the statement. By the way, this picture here is for what? Let's call this moment for t equals 0. I will draw now another picture for t equals 3 seconds, right? Let's also do that. So at t equals 0 moment, the balloon was here at the 65 feet. But now, 3 seconds later, at t equals 3, what will happen? The bicycle won't be here anymore. It will move towards right, so it will arrive somewhere here, right? Bicycle is somewhere here now, and the balloon will be up higher like this. So after 3 seconds, it will also go higher like that. So can we compute these distances? For example, what is this distance and what is this distance? Can we compute them? Yes, we can, because we know this vertical velocity and this horizontal velocity of the bicyclist. So this distance here is, in fact, since 3 seconds passes, this is 3 times 1. And 1 is being the rate of change of y per second. So I will multiply it with 3. After 3 seconds later, this distance will be 3 feet. And here, of course, we will multiply 3 by the horizontal velocity, which is 17. Okay? So this is my picture after 3 seconds later. 3 times 17. And if you use the Pythagorean identity, you will find s as, I guess, 5 times 17 or something. Yeah, something like that. Okay, after drawing this, how did I compute this number for s? Because I use Pythagorean identity. 3 squared and 51 square root gives you that. Not 3, sorry. 68, of course. The total length here is 68. Okay, so far so good?
Yes, teacher.
Okay, after 3 seconds later, your picture will look like this. After 3 seconds later. And we are interested in this particular moment. Don't forget. At this particular moment, we want to find the rate of change of s. In other words, ds over dt. So this is the first step. Understand the question. Now, second step is what? You need to find a relating equation. Relating equation. Now, look at your diagram. You have dy over dt, dx over dt, and you want to find ds over dt. How are they related? Y, x, and s. How are they? Can you give me a relating equation including these 3 quantities? Of course.
Y square plus x square equals to s square.
Exactly. The Pythagorean identity is the desired relating equation here. You're right. Okay. This is our relating equation. Now, third step is take the time derivative of both sides. Always you will follow these steps. Take time derivative of both sides. What do I mean by time derivative? You will take the derivative with respect to t. Okay, don't forget all those quantities y, x, and s, they all depend on t. They are changing in time. So we can derive them with respect to time. How do I do that? By using implicit differentiation. 2y times the derivative of the insider function with respect to t. Similarly, 2x dx dt equals 2s ds dt. Is that okay? Okay,
Yes.
after taking the derivative like this, you can simplify all the 2's. And then, now the last step is to insert what you know at that particular moment. So now I will insert what? I know that dy over dt is 1. I know that dx over dt is 17. I also know the y and x values, also s values from this part, right? From this part. This is the particular moment that I interested in. At this moment, I want to solve for ds over dt. So let's insert all the quantities there. At that particular moment, I solved x as 51. The y distance, the total y distance is 68, you know, this part. Sorry. So 68 is y, this is x, and this is s. I am also inserting all of them. 68 and s is 5 times 17. Let's insert all these quantities that happens in my particular moment. So what do I have then after doing this insertion? Y is 68 times 1 plus x is 51, dx over dt is 17 equals 5 times 17 times ds over dt. You see, after inserting all those values, I have this equation. And from this equation, I can easily solve for this one. So from here, ds over dt is solved as, if you do the computation, you will find this, 11 feet per second. So this shows you that at this particular moment, the distance between the bicycle and the balloon is increasing at a rate of 11 feet per second. Why I am saying increasing? Because we find a positive quantity, okay? If the rate of change of some function is positive, it means that it is increasing. If the rate of change turns out to be negative, this means that that function is decreasing, okay? So these are the main steps that you need to follow to solve a related rates problem. First of all, you will decompose your statement like what is given, what you want to find, okay? This is the first step. Second, you will find a relating equation. Next, you will take the time derivative of both sides. And the last step is you will insert all the given values at your particular moment to solve for what you want to find. Okay? These are main 4 steps that you need to follow. Any questions now? About
No, teacher.
it
It's
should
clear.
be okay, thank you for the reply. It should be crystal clear because related rates problems are really important for engineers. You know, engineers always wonder, like, when do I use calculus in my own expertise, in my own area? Here is your answer. You use calculus to solve real-life problems. Related rates problems is the most important application of calculus course to the real life, okay? You will need this in your professional engineering lives. Okay, I move on. Let's look at this example now before the break. Okay, we have a building here and its height is given as 80 feet, okay? And as sun rises, we are interested in the shadow, length of its shadow, this part. This is the shadow of that building. And we are interested in the length of this shadow, okay? Let's call this length as x of t. Why the length of the shadow depends on time? Because as the sun moves here, for example, the length of the shadow will get smaller. After 1 second later, for example, again, the length of the shadow will get shorter. So the length of the shadow depends on time, obviously. That's why that length should be denoted by time-dependent function, x of t. Okay? So I remove this now. What we are doing here. Okay, so it says that on a morning of a day, when the sun will pass directly overhead, the shadow of an 8-feet building on level ground is 50 feet long. Okay? At some moment, the length of the shadow is given as 50 feet. At the moment in this question, okay, at the moment in this question, the angle theta the sun makes with the ground, theta is here, okay, the sun makes with the ground, this is the angle theta, is increasing at a rate of 0.27 degrees per minute, okay? So, we can start now constructing our diagram, given what is given and what we want to find. Given that, and want to find. So what is given? What is this quantity here? This is the rate of change of the angle theta. It says that the angle theta is increasing at this rate. So this is in a given expression for the theta over dt, rate of change of theta, degrees per minute. But to use this quantity in our computations, we need to change this degrees. This is given in degrees measure to radian. How do you do that? How can you change the degree measure to radian? You do that by multiplying with pi over 180, okay? This multiplication transforms it to radian measure. So if you do this computation now, you will find 0.0015. This time not degrees, but radian per minute, okay? And you have to do that to use it in your computations. It should be in not degrees measure, but in radian measure. Okay, so this is given. What we want to find is at what rate is the shadow decreasing at this particular moment. Okay, so we want to find, that's right, what we want to find. We want to find the rate of change of the length of the shadow, right? The rate of change of this function is asked. So dx over dt we want to find at some particular moment, at the moment when the length of the shadow is 60 feet long. Don't forget, this is also some given information. At some moment, the length of the shadow is 60 feet long, and at this particular moment, we want to find the rate of change of the length of the shadow. By the way, since it is given in the statement, you cannot directly write here 60 feet. I want to warn you on something. Okay, it is given at some particular moment, 60 feet is the length of the shadow. You cannot just insert it to your picture. Why? Why you cannot just insert it? Because it is not constant. The length of the shadow is not constant. It is some particular moment. Instead, you need to give some variable to that quantity, to the length of the shadow. It is time dependent. It changes in time. So it is x of t. But we will, of course, use this information somewhere at this particular moment. We want to solve for dx over dt. So first step is done. We totally understand the statement with all the details. Second step is what? Finding the relating equation. Find the relating equation. Now let's look at the picture. We have theta here. We have x of t here. And we have this constant length, 80 feet for the length of the building. Can you tell me an equation that relates these three quantities? There is one related to trigonometric functions. What trigonometric function relates these three? Any guess? Okay, it is tangent theta function. Tangent theta is the opposite edge divided by this. By the way, why we cannot remove 60 here, but we can 80? sorry, why we cannot put 60 feet to my picture, but we can put 80 feet? Because this is not fixed.
Because yeah,
yes.
it is not constant.
Exactly.
80.
Exactly. Thank you for the reply. 60 is not fixed. It is not constant. It depends on time, while 80 is fixed. It is a constant. That's why you can just put it in your picture. Okay. So let's move on. We find the relating equation, and the next step is take the time derivative. Take time derivative of both sides. So what do I mean by this? You will take time derivative of everything. You start with the most outer function. Derivative of tangent is secant square theta. Then you go inside d theta over dt. And on the right hand side, what do we have? We have 80 as a constant. Derivative of 1 over x is 1 over minus 1 over x squared. Of course, you will multiply with time derivative of x. Okay, this is what we have. Now, we will insert what we know at this particular moment when x is 60 feet long. When x is 60 feet, now we can draw the particular moment that we are interested in. The particular moment when x is 60 feet long, this is 80. There is this theta. So, you know, this spatial triangle, the hypotenuse should be 100. And I need the value of secant theta at this particular moment, right? So from this picture, you know how to compute secant theta. It is 1 over cosine theta. What is cosine theta here? Opposite edge, adjacent edge divided by hypotenuse, right? Cosine theta. 60 over 100. So the result is 5 over 3, I guess. Okay, secant theta is computed 5 over 3 at this particular moment. Now, the last step, inserting your particular moment. At the moment when x is 60, secant theta becomes 5 over 3. We also know the theta over dt from the beginning on. It is given as this number. We also know the theta over dt. It is 0.0005. Sorry, 50. Like this. Sorry, not too many zeros. 0.0015. Okay, this is the particular moment that we want to insert. Let's insert everything. Secant square theta, 5 over 3 squared. D theta over dt is given as 0 times 0.0015. 80, 1 minus 60 squared times dx over dt. You know, in this equation, the only unknown is this. And you can easily solve for it. What do you expect? This is supposed to be positive or negative. Look at what happens. As sun rises, the length of the shadow, is it decreasing or increasing?
Decreasing.
So the rate of change of
Negative.
should be negative, and it is the case. If you do this computation, you will solve for dx over dt as minus 12 feet per second, okay? And this minus here indicates you something. It means that length of the shadow is decreasing at a rate of 12 feet per second. So every second, the length of the shadow is decreasing 12 feet. If you find rate of change as a minus quantity, it means that it is decreasing. If it would be plus, it would mean that the shadow would be increasing, okay? But the minus means length of the shadow is decreasing. So is that okay? Any questions about this solution? I think
No, teacher.
we should go over the steps at this. First, understand the question. What is given? What you want to find. Second, find a relating equation. Third step, take the time derivative of both sides. And the last step is insert the particular moment that you are interested in to solve for what you want to solve for. Okay? There are basically 4 main steps in solving related rates equation problems. Okay. Let me also write here the particular moment, and then we can move. Okay, let's move on to this example. By the way, I will skip this one. This will be an exercise for you. It's a nice exercise. Try it by yourself, please. Okay, this is another related rates problem. And this one now, we will solve it and then we will stop for the break. Let's try to understand. We are videotaping a race from a strand 132 feet above from the track. So this is some fixed quantity. This is the distance of our camera to the race road. Okay, it is fixed. The vertical distance. We are not moving anywhere. We are sitting at the same seat during the race. So this quantity is fixed. That's why we can insert it to our picture. Okay, it says that a car that is moving at a rate of this. Okay, this is the velocity of the car. The rate of change of this distance, right? Now it is time to give some variables to the distances. I will name this part as x, and obviously, clearly, it depends on time. In time, it is decreasing up to this point. After this point, it will be increasing, okay? So x of t. If I name that part as x, what is this quantity? 264 feet per second. It is rate of change of x, right? So let's start constructing our diagram. Given that this is dx over dt. dx over dt is given as 264 feet per second, but you need to be careful on something. Is x increasing or decreasing in time?
Decreasing.
So what we should do for the rate of change of it, what we should put here?
Minus.
Yeah, even if it is given as a rate of change, we are careful enough not to miss this point. Since x is decreasing, the dx over dt should be negative, okay? Okay, this is something important in this problem. Okay, then what we want to find. How fast, okay, let's keep reading. How fast will your camera angle theta be changing when the car is right in front of you? And there is this second part of the question. So we want to find what? Rate of change of the angle theta, right? And we can easily denote it in calculus notation like that. We want to find d theta over dt at some particular moment. What is that moment? When the car is right in front of you. When the car is right in front of us like this, at this particular moment, we want to find d theta over dt. So at this particular moment, what is x?
0.
Yes, at this particular moment, x is 0. What is theta?
Also 0.
Also 0. Thank you. So at this particular moment, we want to solve for d theta over dt. Okay, that's the summary of the question. Here, at this particular moment, x is 0, theta is 0, of course. So now, first step is done. We understand the details. Second step, find the relating equation. Okay, look at this picture. Can you relate x, theta, and this 132 quantity in an equation? If you are dealing with right triangles, you will always use sine, cosine, tangent, this kind of trigonometric functions to relate the angle with the edges. So what is the relating equation here? Again, I think tangent theta, right? Tangent theta is opposite edge divided by this length. Okay, after finding this relating equation, now time to take the time derivative of both sides. Derivative of tangent is secant square, and then you will keep multiplying with the derivative of the insider part with respect to time. And 132 is just a constant there. Derivative of x is dx over dt. So far, so good?
Yes.
Okay, now we are ready to handle the next step, which is inserting the particular moment. This is our particular moment, by the way. Okay, when x is 0 and theta is 0. So I will insert now x is 0, theta is 0, and I also know this thing, right? dx over dt is given in the statement as minus this. And if x is 0 and theta is 0, what is secant theta? Secant theta is 1 over cosine theta. Okay, let's not write theta, but 0. If theta is 0, secant 0 is 1 over cosine 0. What is cosine 0? It is 1. So secant 0 is 1. So this is our particular moment to insert. Insert all the quantities here to solve for d theta over dt. Okay. Secant square theta is square of 1, as we computed here, times d theta over dt. What we want to find is this, 1 over this, times dx over dt, and it is minus 264. Okay, as you can see again, the only unknown in this equation is what? Is this, which we want to solve for. So d theta over dt is, look at your picture, is theta increasing or decreasing?
Decreasing.
Yes, it is decreasing. So we are supposed to find a positive or a negative quantity.
Negative.
It is decreasing, so it should be negative, which is the case in this example. So if you solve this equation for d theta over dt, you will find minus 2 radians per second. As you can see, it is negative. This means that theta is decreasing at a rate of 2 radian per second. Okay? So that's it. Again, we follow the same steps. We understand the question. We find the relating equation. We take the time derivative and then we inserted the particular moment here to solve for what we want to find. Is that fine? Any questions about the solution?
Yes. No, teacher.
Okay, then let's take 10 minutes break at this point.